Hey guys, welcome to Lab 1, and in Lab 1 we're going to be focusing on pulmonary function. And today we're going to be taking different measurements to evaluate lung function. But first, before we get into that, let's talk a little bit about the respiratory system. Okay, the respiratory system helps in breathing. You guys know that, and breathing is the common name for pulmonary ventilation. Okay, ventilation is the amount of air inhaled or exhaled, and it's measured in liters per minute. Okay? And in ventilation, air is inhaled through the nasal and oral cavities. It moves through the pharynx, the larynx, the trachea, and then into the lungs. Then air is exhaled, flowing back through the exact same pathway. Now, ventilation at rest is about 5 to 10 liters per minute, but can exceed up to 100 to 150 liters per minute during exercise, and can actually approach or even exceed 200 liters per minute during maximal voluntary ventilation, which we're actually going to be measuring today. Now, ventilation is the product of what we call tidal volume and frequency, okay? And tidal volume is the amount of air a person inhales in each breath. And that's multiplied by the frequency, which is how many times you inhale every minute, okay? So therefore, ventilation equals the tidal volume times frequency. Now, frequency at rest is about 10 breaths per minute, but at exercise can actually increase to 60 breaths per minute. While tidal volume at rest is about 500 milliliters per breath, but at exercise can actually get up to 3 liters per breath during exercise. Now, the lungs can be divided into two zones, okay? The conduction zone, which includes the trachea and the bronchi, and the respiratory zone, which includes the bronchioles, the alveolar ducts, and the alveoli, okay? And the conduction zone permits airflow into the lungs, but it's not involved in gas exchange, while the respiratory zone is involved in gas exchange between the lungs and the circulatory system, okay? And if we focus in on that respiratory zone, we can observe that it's very uniquely designed to facilitate the most efficient gas exchange possible, okay? It's very important that we have very efficient gas exchange. And our lungs, first of all, have a huge surface area of respiratory zone. We have about 60 to 80 square meters, okay? And that's actually the size of the tennis court, so lots of room for gas exchange. In addition, the thickness of the alveolar capillary interface, or the barrier between the alveoli and the capillaries, or the blood, is very thin, and it's about 0.3 micrometers. And this again is to facilitate the most efficient diffusion possible. Now, what really sums up diffusion of gas between the alveoli and the capillary is Fick's law of diffusion, okay? And this really best describes gas exchange. And it states that the diffusion through a tissue membrane is proportional to, 1, the pressure difference across the sheet, okay? So the diffusion will be greater if the pressure difference across the sheet is greater. 2, the surface area for diffusion. The larger the surface area, the greater the diffusion. And 3, it's inversely proportional to the thickness of the sheet. So the thicker the membrane or the barrier, the less diffusion that happens, okay? Now, pulmonary function measurements, which we're going to do today, like I said, evaluate lung function. And it's really to detect or monitor pulmonary disease or injury. And there's two main types of pulmonary disease, okay? And then we're going to talk about restrictive lung disease and obstructive lung disease, okay? And restrictive lung disease is characterized by the loss of lung compliance, okay? In other words, the lung is stiffer and cannot completely expand. So you can imagine if the lungs cannot expand as much, there's going to be less room for air during each breath. And this is going to result in a decrease in air volume during each inhale and exhale, okay? And an example of this is the increase of fibrosis of the lung, okay? Where chronic injury to the lung, like smoking, produces scar tissue and promotes lung stiffness, okay? Now, obstructive lung disease, the other type, as the name suggests, is characterized by an airway obstruction, okay? And this obstruction can be the result of excessive contraction of smooth muscle caused by inflammation, and it results in the narrowing of the bronchi and the bronchioles, okay? And because of this narrowing of the airways, airflow is obstructed. In other words, the flow of air during each inhale or exhale is decreased, and a person with an obstructive disease must work harder to inhale or exhale a set volume of air, okay? Now, moving on to how we test these is the most common method of measuring lung function is through spirometry. Okay, and spirometry is the measurement of the movement of gas into or out of the lungs during various breathing maneuvers. And we can do this using a spirometer, which captures air being breathed out. So today, with our spirometers, your group will be testing static lung volumes and dynamic lung volumes. The static lung volumes are not affected by the rate of air movement in and out of the lungs. Okay, it's important to remember. But while dynamic lung volumes are, however, affected by the air flow out of the lungs. Now finally, you're going to repeat these static and dynamic tests while mimicking an obstructive disease, okay? And the airway in your spirometer will be narrowed, decreasing the rate of airflow. So then you're going to compare the obstructive values to the unobstructive values and make an assessment on, well, what tests, is it static, is it dynamic, is it both, that are really affected by this obstructive.